This is a video on applications of EM waves in night vision devices. It is presented by Tinish Bhattacharya and Shridu Verma.
The night vision goggles were initially developed for spotting enemies and surveillance at night and in dark areas. These days, the uses have been extended to tracking suspicious targets and also for navigation. The night vision goggles are also useful for tracking the recent changes in the environment. Like, for example, a recently dug up region will look different in the goggles than the surroundings.
So, how does it work? It works on two basic technologies: image enhancement and thermal imaging. So, image enhancement works by collecting the tiny amounts of light, including the lower portion of the infrared light spectrum that are present but may be imperceptible to our eyes, and amplifying it to the point that we can easily observe the image. Thermal imaging, on the other hand, operates by capturing the upper portion of the infrared light spectrum, which is emitted by as heat by objects, instead of simply reflected as light. Hotter objects, such as warm bodies, emit more of this light than cooler objects like trees or buildings.
The electrons in the atoms, when heated, jump to a higher energy level, and when they return, they release energy in the infrared region. This infrared energy is detected by our night vision goggles to map the environment. There are three infrared regions. One is the near infrared region, second is the mid infrared region, and the third one, which occupies majority of the infrared spectrum, is the thermal infrared region. Now, the difference between the thermal infrared region and the other two regions is that the thermal infrared waves are emitted by a body instead of being reflected from it, which is the case for the other two infrared waves. Night vision goggles majorly uses these infrared waves to map the environment.
So, how does thermal imaging work? Firstly, a special lens focuses the infrared light emitted by all of the objects in view. This focus light is scanned by a phased array of infrared detector elements. The detector elements create a very detailed temperature pattern called thermogram. It only takes about 1/30th of a second for the detector array to obtain the temperature information to make the thermogram. This information is obtained from several thousand points in the field of view of the detector array. Now, the thermogram created by the detector elements is translated into electric impulses. The impulses are sent to a signal processing unit, a circuit board with a dedicated chip that translates the information from the elements into data or for the display. The signal processing unit sends the information to the display, where it appears as various colors depending on the intensity of the infrared emission. The combination of all the impulses from all of the elements creates the image. There are two common types of thermal imaging devices: uncooled and cryogenically cooled. The uncooled ones are the most common type of thermal imaging device. The infrared detector elements are contained in a unit that operates at room temperature. The cryogenically cooled ones are more expensive and more susceptible to damage from rugged use, so these systems have the elements sealed inside a container that cools them to below 32 Fahrenheit or 0 degrees Celsius. The advantage of such a system is the incredible resolution and sensitivity that result from cooling the elements.
The second technology employed in the night vision goggles is the image enhancement technology. Now, this is achieved by using devices called night vision devices, or NVDs in short. These NVDs are comprised of an objective lens and an image intensifier tube. The objective lens is used to get the light from the surroundings, and image intensifier tubes is used to increase the resolution of the image. The image intensifier tube is shown in the figure. It is comprised of a photocathode followed by a microchannel plate, or MCP in short. The electrons from the MCP are incident on the phosphor screen, which creates the photons which are visible in the NVD image. The photons from the unenhanced image strike the photocathode. Now, due to the high applied voltage, the electrons produced by photocathode move towards the MCP, or the microchannel plate. Now, this MCP is a glass disc with huge number of microscopic channels in it, which are made using fiber optic technology for easy passage of the electrons. These channels are not straight, they are little tilted so that the incoming electrons strike with the atoms of the MCP and in turn produce more electrons. Now these electrons will again strike with other atoms and produce more electrons, thus setting off a chain reaction. Thus, the MCP multiplies the number of electrons corresponding to a pixel value in the image to be enhanced and thus helps increasing the resolution and clarity of the image. The tilt in the channels of the MCP also ensures that ions don't pass through. Due to high voltage and well-defined channels in the MCP, the electrons maintain their positions with respect to their respective channels and thus no significant image distortion occurs. These electrons are made incident on a phosphor screen. These phosphors create the green image on the screen which can be viewed through a lens.
Now we will talk about the generations of night vision devices. Generation 0, which started around World War II, was first created by the United States Army and used active infrared. This means that a projection unit called an IR illuminator is attached to the NVD. The unit projects a beam of near infrared light similar to the beam of a normal flashlight. Invisible to the naked eye, this beam reflects off objects and bounces back to the lens of the NVD. These systems use an anode in conjunction with the cathode to accelerate the electrons. The problem with that approach is that the acceleration of the electrons distorts the image and greatly decreases the life of the tube. Now Generation 1, which was heavily used in the Vietnam War, used passive infrared instead. Once dubbed Starlight by the US Army, these NVDs use ambient light provided by the moon and stars to augment the normal amounts of reflected infrared in the environment. This means that they did not require a source of projected infrared light. Generation 2, which started around the Gulf War, had major improvements in image intensifier tubes resulted and hence it resulted in improved resolution and performance of Generation 1 devices. The biggest gain in Generation 2 is the ability to see in extremely low light conditions such as moonless light. Generation 3, which is currently used by the US military, while there are no substantial changes in the underlying technology from Generation 2, these NVDs have been better resolution and sensitivity. This is because the photocathode is made using gallium arsenide, which is very efficient at converting photons to electrons. Additionally, the MCP is coated with an ion barrier which dramatically increases the life of the tube. And Generation 4, which is strictly not sold outside the US, uses filmless and gated technology, which shows significant overall improvement in both low and high level light improvements. The removal of the ion barrier from the MCP that was added in Generation 3 technology reduces the background noise and thereby enhances the signal to noise ratio.